Right, good evening, everybody. Welcome to the BRLSI. This evening is, in fact, the inaugural lecture in a new BRLSI subject interest group in sustainability. I'd like to encourage anybody who's here or listening online who's interested in this to get in touch with me, which you can do through the BRLSI, and that way maybe if you'd like to contribute to organizing the activities of the new sustainability group, we can take account of your interests and maybe you can actually get involved yourself. So to inaugurate the proceedings of the new sustainability group, we're very lucky to have with us this evening Pete Walker, who's long been my colleague at the University of Bath. And Pete is Professor of Sustainable Building Materials. Is that right? Innovative construction materials. And he's in the Department of Architecture and Civil Engineering at the University of Bath. And actually, Bath's quite strong in this area. And that's very much due to Pete's influence. He's been at the university, he tells me, for 26 years now. And he's going to tell you all about what he's been doing in those 26 years this evening, trying to shift the pattern of construction of new buildings in the UK to something a bit more sustainable. Welcome, Pete.
Thank you very much, Stuart. Thank you all for coming, particularly in the weather, and it's a pleasure to be here. And so, as you can see, I'm going to talk about well, not just hazardous straw, but certainly use of bio-based, plant-based building materials. And some of this research has indeed been taken, not quite 26 years ago, but some of this research relates to work that's been undertaken over the last 15 or so years. In that joint Department of Architecture and Civil Engineering, I'm a civil engineer rather than an architect. So I'm going to talk about some of the technologies, background, drivers, and some of the research work that I've been lucky enough to be involved in over those last 26 years. I mean, normally I would like to be happy to take questions as we go and stop me, but I think because in the respect of people online, we'll have to wait until the end so we can have a roving mic and the people who are not in the room can hear your questions. So we'll wait until the end there. So hopefully this is going to change a slide. Oh, that's not a good start. Right, go on. There we go. Right, so I mean the background drivers, and many of you may know, I know there's some colleagues in here, former colleagues, current colleagues, and some friends in here. So some of this information will be very familiar, but just to pinpoint the impact of construction in relation to much of the drivers of the work I've been involved in is around driving down carbon emissions associated with construction. So buildings, the construction of buildings, the operation of buildings is around 40% of our total emissions, and the construction industry in its size in the UK is estimated to consume around 60% of all materials. The second most consumed material on the planet after water is concrete. So we use a lot of building materials. And that has a huge impact both on resource use and non-renewable resource use, as well as waste as well. And so, I mean, to separate buildings and the construction industry, so the industry that creates the built environment is responsible for about 10% of greenhouse gas emissions through manufacture, through construction, demolition, etc. And so related to that is also an increasing recognition. A lot of the work that I've been involved in has been around building new buildings, but now increasingly the work is about retrofitting and remodeling existing buildings. As the second bullet point says there, around 80% of the homes that will be occupied mid century have already been built. So 25 million homes or so need to be improved, retrofitted to make them more suitable for and lower carbon in their operation, but also improve the quality, the health, etc., of these building spaces. And it is a priority for the UK government, but equally the size of that challenge is enormous. There are simple things that we can do, but to deeply retrofit all of the homes to make them zero or near to zero carbon is a massive challenge, combined with the fact that we've got climate change, we've got increased flooding, we've got expected maybe milder winters, but increasingly warm summers. So in some ways, whilst design of buildings in this country has largely been driven by winters and keeping buildings warm during winter, now increasingly we're also looking at cooling during summers as we expect warmer and warmer summers with climate change. So improvements to reduce operational carbon. So this is the operation used for heating and increasingly cooling of buildings, as well as general operation, lighting, etc. To improve, as a result, consequently, by making them more energy efficient, reduce running costs in light of cost of living crisis as well, in terms of making buildings more affordable, particularly social housing, and improve the quality of some of the building stock as well, and to also, as I'll touch upon later, make them healthier for the occupants as a consequence of that work. Now, this lecture and the invitation from Stuart is to talk about bio-based construction materials, and particularly around work on straw bale construction, but some of the rationale and what's been driving interest in use of bio-based building materials and moving away from likes of concrete and stone and brick masonry and steel and other forms of construction and construction materials, and using alternatives. One bio-based building material that is widely used and is a mainstream construction material in this country is, of course, timber, trees. We harvest trees, and that is a bio-based building material. But much of my research has been around looking at other bio-based, plant-based building materials. And one of them is around reduced GHG, greenhouse gas emissions, because in particular, if you can account for responsibly the photosynthetic carbon that these plants absorb. So around 1 kilogram of straw will absorb around 1.8 kilograms of CO2 to produce it in photosynthesis. So it's a carbon store. There's a challenging argument to get about what the end of life scenario is that is. So ultimately the material breaks down, it will that carbon dioxide be re-released, but it's providing a temporary carbon store at a time then we really need to get carbon emissions down. And through their use also, hopefully they reduce operational carbon and energy use as well. They're renewable, ideally, and hopefully they also reduce waste as well, as increasingly look to solutions that are part of circular economy and circular construction. So it's not linear, use it, throw it away, dispose of it, but we keep it in use. The photograph here is one of the tallest timber buildings in the world. I think it's about 18 stories high or so, built of engineered timber, cross-laminated timber and glue-laminated timber. It's at the University of British Columbia in Vancouver. And increasingly there are moves to build taller and taller buildings out of timber instead of concrete and steel. Also, as we'll see, bio-based building materials improve the building environmental performance through concepts known as hygrothermal performance and vapor permeability, which I'll touch upon, which can lead to healthier buildings. And also with things like straw, it's providing new markets for agriculture and farmers as well. So some of the bio-based construction materials that I've touched upon at various points in research over 26 years, including timber and wood-based products, and many of these have a traditional vernacular use. Many of these can be dated back millennia in the use of these materials, whether it's straw in mud bricks, for example, or straw as thatch or reed as thatch, etc. They have a long tradition, and many were widely used and then displaced during primarily the Industrial Revolution. Particularly, straw is a co-product of food production, which is not unique, but is one important differential from some of the other bio-based building materials, in the sense that We are growing wheat and we're growing barley, etc., to produce the food, and a co-product of that process is the straw, which we can use in a variety of uses, including in construction. Whereas some of the other materials like hemp and flax is grown primarily for the hemp and the flax. So that land is being displaced from food production towards agricultural sort of crop production. Bamboo, of course, very fast growing plant. Reeds traditionally used, and in recent years, increasing interest in the use of mycelium as a building material, particularly using the mycelium of the fungus to lock together other aggregates to produce insulation materials in particular. And there's a current PhD project ongoing that one of my colleagues is supervising. That's plant-based, and of course, looking at bio-based, then there are animal-based products. Sheep's wool is probably the most well-known, but horsehair has been widely used in plasters. So many of the plasters in the buildings around Bath, the traditional lime plasters, will probably have horsehair or some other hair in them to help with the cracking, etc. And of course, traditionally, as additives, some of the other plant-based, animal-based products have also been incorporated into earthen construction. And normally I might bring some samples along of these materials, but not of the last bullet point there generally. And then increasingly, my colleagues have been looking in the last 10 years at the use of bacteria as well. And calcite-forming bacteria is a way of self-healing concrete, incorporating bacteria within the concrete mix, which will be activated at the point that the concrete might crack. And concrete generally, at some point, will crack during its life. The role of the steel in reinforced concrete is to carry the forces across those cracks, but to heal it. Oh, there's some people in the lobby. Sorry, the people in the lobby. So first of all, just talk about straw bale construction. So straw has been used in construction for millennia, but straw bale construction is relatively new. Late 19th century is the way sort of books on straw bale construction go, with the invention of mechanical baling machines. So prior to that, straw was manually baled. So this is one of the earliest straw bale buildings still in existence. I mean, obviously that photograph is quite old. That's probably a Model T Ford or something like that, taken in the 1920s or so. It's still in existence, and it would. The story is that they were built in Nebraska, in the plains of Western America, where there was growing wheat and other crops, and there weren't many other building materials. The plains are pretty much denuded. There's no trees or as such. And so they saw the opportunity of building buildings with these bale machines, with bales, which when they brought the baling machines in. And that lasted for a few decades until eventually the road and rail infrastructure improved enough that then they brought other materials in from further afield, from factories, etc. And straw bale buildings, as far as I know, didn't really arrive in the UK until the 1990s. The first sort of straw bale buildings we saw. And straw bales can be used as load-bearing construction, i.e. they carry the weight of the roof and the floors in a building, like it's dry stack, like masonry construction, or can just be used as infill with another structure, typically timber, or indeed can be in a prefabricated form of construction. We'll go through each of those. Now here's an early European example of a straw bale building. This photograph is recent in the last few years. So this building is now over 100 years old, or I think it's about 60 kilometers outside of Paris. Now, I mean, you can't see, of course, the straw bales. The bales they're incorporated within a timber frame structure and then lime plastered over it. And then they've allowed this sort of Virginia creeper or some vine to grow over it as well. And it's now a protected building for its historical significance in France. Why straw bale construction? Well, the bales themselves provide remarkably good insulation. Their thermal conductivity isn't as low as some other insulation materials. So to get to the same thermal protection or thermal insulation, you need thicker walls using straw bale than you would with some other insulation materials. But because they come in that size anyway, you get very good thermal insulation if you can tolerate walls that might be 45 centimeters or so thick. They're cheap. The bales themselves are cheap. They store this biogenic carbon, this photosynthetic carbon. They're renewable. They're a co-product of food production, and in the UK, they're widely available wherever there's cereal farming. I mean, interestingly, most bales I've used in research and projects come from straw bale merchants rather than from the local farmer. So sometimes they might be merchants who are based in east of England, and we are moving straw across the country rather than going down the local farmer, mainly because of the quality of the bales and the density of the bales that they're made. But there's no reason why you can't use local bales. And so this is a house that I think is built in Somerset. And you can see behind the scaffolding there. Unfortunately, I don't have a photograph of it completed, but that is load-bearing straw behind there. Interestingly, you don't see many examples where the bales have been cut to take that sloping roof as well. But it's two-story building built where the external walls are made from straw. And you would only really use the bales on the external walls, because that's where you want the thermal insulation on the outside of your building. And then there's another building here. This was social housing built in Lincolnshire with a two-story load-bearing straw bales with a lime plaster over them. And then infill is a little bit easier. This is in Belgium, an engineered timber frame building, and you can see perhaps the straw hiding inside the building there. And the advantage of this technique is that you can protect the straw from the weather if you get inclement weather during your construction. And here's another example. This building, I took this photograph about 20 years ago on the outskirts of Helsinki. And from that basis, you wouldn't know that that was a straw bale building. It shows it's got a very similar timber cladding as the other houses that were on that estate. And it's really, if you look at the depth of the window reveals that you can actually sense that the walls are a little bit thicker than some of the other buildings around there. And then it's not to be, not just North America or Europe, which are sort of scenes of center of straw bale construction, but you can find examples around the world. So this is in China, and this is a PhD project that was completed, 9 years ago now. And this is using straw stacked in between brick columns there, a very simple building, and really the walls are just, the straw is being stacked there vertically. So you have important to space those brick walls, columns at the right distance apart so the straw will stack in. But it does still illustrate a particular example of problem with straw in this sense, is that you could stack these up here, but you want them tightly fitted so there's not any air gaps. You want good air tightness and good continuous thermal insulation. And so there's always going to be a gap here because to fit the last one in. So in this case, they have just manually stuffed or pushed straw in just to fill that gap up. But when I come to look at mod cell, we'll see how that was solved. So the bale house was built in September 2009, and that's its original location on the University of Bath campus. And at the time, the director of estates told me, yeah, that'll be fine. You can leave it there 20 years. We're not got any plans to build on that site. And then 2 years later, they said, well, actually, we have got plans to build there. And so that's, if you know the university campus, that's where the Chancellor's building is. And so that's sort of the east end of campus. And so the building was taken down, dismantled, and moved about 80 meters to a new site, which I'll show you in a few slides' time. But in this case, the panels at the top are, if I can get the cursor to come up, this is their second location already, because those panels were used in Grand Design's live project prior to being used in the bale house. So they've been, if you like, moved 3 times now. And you'll notice the difference when the photograph later. But the building reads as, there are panels here, and the panels are either completely straw and lime plastered or semi-glazed and with straw, or in this case, this panel here, are completely glazed with a door. So the panels are prefabricated off-site, and then brought on site and craned into place, and means that the construction time on site is very fast, and the other benefits in terms of quality construction, safety, and also risks of being delayed in construction by inclement weather, because we all live in Bath or close to Bath, so we know there is no dry season. It rains pretty much the same every month in Bath. And sort of looking at historical, when the wettest month is August, and the driest month, anyone? February, but I reckon that's only because it's 28.25 days long. So I think that, on average, the daily rainfall is pretty much the same across the year. I mean, obviously, temperatures, amount of sunshine, drying, etc., changes during the seasons, but the actual amount of precipitation that falls out of the sky is pretty much the same. So in the case of the panels at the base here, these 8 panels, they were made off-site in a farm just near South Stoke. So literally 3 miles or so or less from campus. And so the materials to make the panels were delivered to this farm. And basically, primarily all you need is cover, some plant for lifting, a tractor, a forklift ideally, and some water and stuff to mix the lime plaster. So the panels are made from these engineered timber frames, and they're glue laminated or cross laminated. So that's softwood, pine, glued together to form an engineered form of timber, which is dimensionally very stable. And it comes pretty much flat pack style, if you like, this sort of IKEA flat pack, and you make it in the factory here, which at the time is called a flying factory, because you only set it up for the time that you need it. Those pieces of timber are not light, but I mean, 2 people here can make 1 panel roughly in a day, up to the point of getting ready to lime render. And you can see that there are holes already drilled here for the other bolts and other bits and pieces, sundries that go in there. So make the panel up and then set it upright, and then there's a small amount of steel here that acts as bracing to keep the panel plumb, true. And then the straw is fitted in there, and the straw is laid in the same way as if you were laying bricks. So it's coursed, so the vertical joints are broken, which means the bales are halved for this second course here, which is easily done. You can quite quickly restring a bale and make 1 bale into 2 half bales. The nominal size of a straw bale is 1 meter long, and that varies plus or minus 10 centimeters. So in tolerances compared with other construction products is quite poor. And so you can tolerate that in prefabricated construction to some extent. And these panels are 3 meters wide internally in the frame and 3 meters high or so. And then you can fill up the panel with the straw, and you want it complete, no air gaps. And so to overcome that problem with the gap at the top, initially these panels were made as a U shape, and the top was left open. So that top piece of timber there was left off and it's stacked. And then the idea was that you place it on top of the straw, and then using these vertical steel bars here, you can just about see them. They're threaded, that you would tighten nuts and bring the whole thing down to tighten it. And then someone realized, well, that's a faff, and this also requires you working up a ladder at height. And if you tighten 1 nut, then another one goes loose and you want to bring it down evenly. So the panel was made up, and then I don't actually have an image of it, but the solution to that problem of getting it tight was to fill it up to the penultimate course here, and then bring a forklift truck in and push and squash all those courses down, slot in the last set of bales, and then withdraw the forks, and it would be nice and tight. And that made it a lot quicker and easier. And then once it's like that, then a little bit of trimming of the straw, and then lime plaster. In this case, lime plaster went directly onto the surface of the straw, and then a second coat went there. It's done in 3 coats, and it was possible to do everything off-site, but the final coat actually goes on-site, or it was, because inevitably with the lifting and the moving, you get some damage to that surface during. So a final finish coat to give the best quality finish was done once the panels had been moved, lifted on site and put in place. And there it is again, and there it is as it was yesterday. And you can see the coloration difference, I think, hopefully between, you've got some, basically some cover mold on there, particularly these ones I've colored differently to the ones on the ground floor. And I think it is because of their age. Now, this has provided us with a research facility that our students have worked on since the last 15 years. So we've been measuring the condition of the straw inside the building, and the straw is remained dry and is remarkably good condition. It's as, you know, if you cut the plaster off with a little disc, it's still fresh and golden as it was when it was first built. So that's good. I mean, I think because architects always like to show the buildings when it looks like this, fresh, and then the Western red cedar wasn't treated. It could have been, but it was decided not to treat it, so it has grayed off like it has there. I mean, that netting there is just to keep seagulls off, I think. And it has changed orientation since in its move of 80 meters from one side over to where it is at the moment now. And it's now, originally it was done as a prototype 2-story house, and it's now used as offices by the estates department of the university. And I mean, it was designed, the top floor was designed to be, basically it's an upside down house in what we would conventionally think of a house. So the bedrooms are on the ground floor and the living area is on the top floor. And it's an open plan living area, kitchen, living room, and it was designed to be naturally ventilating. But in turning the office, making this into an offices where I think about 8 people work in there now, they've subdivided it up, so they prevented the cross ventilation. So I think it is comfortable. They like it. To asking the people who work in there, they like it in the winter. In the summer, if on a really hot day, they can struggle a little bit. You can overheat in the summer, and that's because the loss of the ventilation. So that's something that they need to look at. I mean, a little bit of lime wash, a quick paint, and that would freshen that plaster up, no end. So just a little bit of maintenance. Otherwise, the building is in good condition. Now, inevitably, talking about straw, the 3 little pigs are mentioned. And there's even straw bale building companies around the world that have called themselves Huff and Puff Construction and such things. And the reason for showing this image, this is on a farm just outside of Bath. The building was built, I think, about 2002, something like that. And it's a small, simple, load-bearing straw bale building. But it is one of the image issues around straw bale. That inevitably, you mentioned straw bale, and you mention the 3 little pigs, and the big bad wolf will huff and puff and blow it down. And that does enter into the psychology of, you know, a straw. Is it going to rot? Is it going to be blown away in a hurricane? Is it going to burn down? And is it going to be full of rats? And these are the kind of things that people will raise. And that's one of the challenges and things that we've been looking at in our research as well. This is a map of the latest map from the European Straw Bale Building Association. It's not a complete map, but it shows a location of straw bale buildings in Europe, of ones that people have registered. Now, the number shown there for the UK, or primarily that's England and Wales, is certainly, the number is significantly more than there. Because I don't think potentially, I suppose this one might be the bale house, but there's at least 3 or 4 straw bale buildings in Bath. So it's an incomplete register, but I think it's just occupants, people who wish to register their own buildings. But there's certainly a big concentration in France in particular, and here in southeast France, there's a lot of straw bale buildings there, but also over there around Czech Republic and Eastern Austria as well, a lot of straw bale buildings. And I think overall, I mean, in the UK, I think the number of buildings now is probably in the region of 300, which that certainly map doesn't reflect. I think in France, it's well over 1,000 straw bale buildings. Still small compared with in the UK, the 23 million or so tin, masonry and concrete houses that are here, but it's progressed a lot in the time that I've been working on it, but there's still a lot of more work to do. So some of the outcomes of the Bale House was this project here in Leeds, which I think was completed around 2010, 11, is Lilac Housing. It's a housing community trust. There's 23 apartments or flats there. And I mean, because at the time, one of the issues did change, but at the time, the panels didn't carry certification. So they weren't certified by an independent third-party certifier, which as a consequence, it was difficult to get warranty from an insurer. And if you can't get warranty, you won't get a mortgage because a bank won't lend you against something that they feel if that's not got warranty. So that was one of the barriers to this. And the process, so putting the straw bale panels, mod cell panels through, I mean, we did get them certified, which means you can get warranty, you can get insurance. But at this time, these people did it with they were cash buyers essentially. They didn't rely on mortgages to be able to fund this, and that's why a lot of the projects were done that way. Now, some of you may be familiar with this building. It's at Hayesfield School on Broomhays, a lower school. It's a science block. And I think to reflect the science block, you've got the DNA helix etched into the surface of the lime plaster. And what differentiates this building a little bit from the others that I've shown is in this case, and with the Bale House, you can read, architecturally, you can read it as panelized. You can see the panels by the way the Western red cedar surrounds of those. Whereas in this case, it's been done and plastered over to disguise the panels, but it's still a panelized form of construction. And then you can also clad them in brick if you want to. This is in Shirehampton in Bristol, along the sort of Portway. And these homes were built, I think, 2015 or so. And as well as being clad in bricks, just one layer of bricks, the other standout thing about these was that they were, as far as we know, the world's first commercially developed straw bale homes, in the sense they were built by a developer to sell on the open market, because the product had warranty. It was certified and had warranty, so people could draw down a mortgage to be able to buy these. So these were put on the open market for sale, and so a developer built these, and they're built next to sort of post-war brick housing. So there's the original, one of the buildings is here. So the planners required them to fit in with that sort of 1950s sort of masonry housing. But I mean, often, I mean, that example in Bristol is a sort of suburban area. Often straw bale buildings are being seen as sort of like isolated buildings in the countryside. But here's an example from Amsterdam of a prefabricated panel, very much in an urban city centre location. And as far as I know, this is the tallest straw bale building I know in the world, which is 7 stories of, again, modular panelised construction. Now, following the Grenfell disaster, we were not allowed to build straw bale buildings this high. There's a limitation of 18 meters on such materials. So we wouldn't be able to build this building in the UK at this moment because of the limitation on flammable construction materials above essentially 18 meters, you get maybe to 5-6 stories. But moving on, I'm not just talking about straw, I'm going to talk about a couple other bio-based construction materials, and one is hemp lime. Now, hemp has been used in construction like straw for centuries, and of course it was a very important fiber for rope making, for textiles, etc., for centuries. And then by the 1930s was discredited. And one story goes, one opinion said that the producers of DuPont and others who made nylon and rayon and synthetic fibers discredited one of the major competitors, hemp fiber, by associating it with marijuana, because the hemp plant is a cannabis plant. And so it basically stopped growth of hemp right until really the 1990s, from sort of 1930s, 1940s to the 1990s, certainly in North America and in Europe. And you can still only grow it now under license. And it's sort of one of the sort of votes of confidence in hemp lime construction, if you like, is that one of our most well-known supermarkets built this building, I think in about 2012. That's in Cheshire Oaks in Warrington, in the northwest of England. And under that time, I don't know if they still have it, but at the time they had this scheme to reduce their carbon emissions by saying that there is no plan B, there's only plan A, so a bit like there's no planet B. And so this building is clad in hemp lime panels. Now, this is a car from 1941 where the panels are made from hemp fibers. And the reason why hemp came back in the 1990s is because the German car industry were also starting to make cars. Mercedes and BMW were interested in using hemp composites, particularly for internal paneling, door panels, dashboards, etc. So that supported growth of hemp plants in the UK and of course, particularly in France. France in particular is where a lot of hemp is grown. This is a picture from, I think, Essex or Suffolk, where a lot of hemp plants have been grown. In the sort of 2008 is probably this image here, and the plant is the second fastest growing plant, crop, anyway, crop, maybe not plant, but crop in the world, next to bamboo, and it can grow up to say 4 meters in about 4 or 5 months in this country. So it's very fast growing. And so it's being harvested here sort of late August, early September. And then what's most, I don't have an image back, but it's the fiber, which is the most valuable part of the crop, is on the outer part of the stem, and that's stripped away to make textiles or fiber composites. And what you're left with is about 60% of the mass of the plant, which is what's called the hemp shiv. And that's the bioaggregate that is mixed together with lime and water to make material like this, which is when it's freshly mixed together. And then it's placed it's usually placed inside, tamped inside formwork like that. So it forms a insulation, biocomposite insulation material. So there's temporary formwork there, or you can use it to make blocks, masonry blocks. He's not very happy in his work, but making this particular building here, which was Adnams Brewery building, again, I think 2009, 10, something like that. It's their brewery that they wanted to store their beer over in Suffolk. Whilst it's primarily a steel frame structure with engineered timber roof and planted roof there, these walls here are made from hemp lime blocks and also insulated. They're called diaphragm walls. So you've got denser blocks here, and then inside, this chap here is tipping his bucket of mixed wet hemp lime. There's insulation in there as well. There's a pattern coming here because same with straw bale, then prefabricated hemp lime is really developed, and the benefits of prefabrication again come down to potential problems with weather during construction, higher quality construction by making it off-site, faster construction, so reduced site times, etc. And so this is timber frame panels filled full of hemp lime and other insulation material, and finished off with a membrane. And then this is the M&S building going up. And often in working on these materials, I've worked with entrepreneurs who I really admire because they take huge risks. They worked with Marks and Spencers on delivering these panels, They'd never really done it before. They're confident they could do it. And you can imagine dealing with Marks and Spencers. There were huge penalty clauses in the contract if they failed to deliver on time or there was a problem with the product, but they still took that risk and delivered this to demonstrate that they could do it. And it's, you know, it's been very successful and an award-winning project. And it's the hemp line panels here are cladding this steel frame structure. And then they've moved on to really into this, the company is Green Core Homes, particularly operating around Oxfordshire, where you get these homes here, again, built in the same approach of prefabricated panels with hemp lime. In this case, obviously quite a high-end luxury home, but also smaller homes and stuff are also possible and available. And there's a number of homes were built the same just after the project, this project in Suffolk and also in Swindon as well. Done some work with cork. Cork, the bark from the cork oak tree, which is harvested and obviously used for bottle stoppers and many other uses, and also has potential for use as a building material and has been used as a building material for years as insulation. And this cork house here was visioned by the architect, Matthew. He wanted to build a building that was completely, the envelope was completely cork. And did it so the roofs are corbelled to be of cork as well. So you've got this sort of unique roof structure, but they're lined here with timber to provide extra weather protection so the rain doesn't come through. But they're individual blocks that are profiled and dry stacked and cut to form the external wall envelope. And it's a highly insulated wall envelope. And also, it's, of course, internally, it's one where you never need a notice board because you can pin up your notices absolutely everywhere if you don't dry on it. And then another area where natural bio-based building materials have made a particular inroad is in natural fiber insulation. So whether that's in terms of sheep's wool insulation, wood fiber insulation, hemp flex, sisal flax, cellulose, blown cellulose, and cork, and all of these are used as insulation materials. And in some ways, this is the least or the lowest risk approach to using these materials because you're not using them structurally. Now, natural fiber insulation products do have a reputation, as it says there, for being not what with an insulation material. Ideally, you want a material that has the lowest thermal conductivity you can get because you want it to be as thin as possible and to maintain the heat, particularly in the cold season, inside the building, and also protect from the heat outside the building in hot periods, perhaps as well. And so many of these materials here don't quite have the same insulation qualities, thermal conductivity values as some of the standard rigid foam insulation or mineral will, but some come pretty close. But they do have other characteristics, and I've got one eye on the clock and realizing that I need to speed up a little bit. So one aspect of using natural materials is something that people refer to as breathing wall construction. Now, and that's a bit of a misnomer because the wall breathing suggests an exchange of air or oxygen and carbon dioxide in your lungs, and that is not an accurate reflection of what a breathing wall is. A breathing wall is one that allows water vapor to diffuse through it, through porous materials. So a breathing wall is one where moisture in a form of water vapor can pass through it, which is advantageous for the quality of the space inside the building and also for the durability of the materials, perhaps in the fabric of the building, in the sense of not storing moisture, which can be deleterious to some building materials. And then also, some of these materials are moisture buffering in the sense that they absorb moisture, they respond to the humidity of the environment they're in. So if the humidity goes up, the building materials mass will go up because it will absorb some of the moisture from the atmosphere. And in the same way, if the humidity goes down, then it will release some of the moisture back into the atmosphere. And as a result of that, it has the effect of buffering the moisture. And as we'll see in a moment, ideally you want to maintain a fairly stable humidity levels in your building, not too high, not too low. And this experiment here is measuring the moisture buffering potential of 2 pieces of clay plaster in response to these stepped changes in humidity between, in this case, between 50 and 75% relative humidity over time. I'm going to skip that one because I am slightly aware I'm going a bit slower but it's important, particularly in these aspects of both breathing wall and moisture buffering are also important in relation to the quality of the building as well in relation to our health. And not only, I mean, this is also combined with things like, obviously, a very important part of buildings also ventilation as well. So movement of air, but avoiding problems with condensation and problems with buildup of moisture in buildings. And this, this very famous case, the tragic case from 2020, where this young 2-year-old died, and the coroner directly related his death to black mold in the flat he lived in, related to condensation. So increasingly, the health of buildings is becoming more and more important. I think this always has been, but more and more aware. And this simple graph here, or hopefully simple to understand, shows the these are different agents, if you like, or actions. So growth of bacteria, viruses, fungal growth, mites, and other things that could be deleterious to our health, and their activity or response to different humidity levels. So if we've got very dry environments, then some bacteria and viruses like those very dry environments. And if we have very moist environments with humidity levels at 80–90%, then of course some fungi and molds and mites and other types of bacteria like those. So there's, if you like, something of a sort of Goldilocks zone here, where it's just about not too hot, not too cold, but just right, where the humidity, if you can maintain the humidity levels between sort of 40 and 60%, then that is considered most beneficial in terms of providing a healthy space for us. And that is through the use of the building materials and the structure, but also, of course, through ventilation and heating systems as well. In relation to one response that bio-based building materials, and this experiment is particularly related to hemp and lime, but it could be other bio-based building materials, is something called decrement delay, or the response of the building materials to changes in environment. So in this experiment here, this is a panel, I think it's 300mm thick panel of hemp and lime, and you saw that composite material being made earlier, and it's in a room which is held at 20 degrees centigrade and 60% humidity, and it's strapped to a chamber that is also initially set at the same conditions as the room. And then in this experiment, the conditions in the chamber were reduced, and we simulated a thermal shock across the wall. So the conditions were maintained constant in the room surrounding it. So essentially the room represented on this side of the panel the internal conditions of a building, and then in the chamber was the external conditions. So we've got a frosty day. And this graph here represents the temperature measured across the width of the panel. But rather than showing it as 0 to 300mm, it's been normalized. So 1 represents 300mm. And what we're particularly interested in is how long it would take, because you'd expect it to reach a stable linear or near linear gradient, thermal gradient from 20, which is that inside temperature, to I think it was 1 degree or so on the external. But the interesting thing is it took 336 hours to get to that position. So that in the sense the speed of change is so slow, you're getting essentially a hygrothermal inertia in that wall. So and we never reach steady state conditions because of course the temperature and weather outside our buildings is changing all the time. So in that sense, you'll have experienced this going into, say, a medieval cathedral and church in maybe Renaissance building in Italy or somewhere on a hot day. The thermal mass of that building means it's much cooler inside there than it is outside in the direct sunshine. And in some ways, this effect is similar to that. We also did an experiment where we did it with mineral wool, which is a common insulation material, and it took 24 hours for it to respond. So in that sense, the decrement response, the delay in responding to that thermal change is a very significant benefit of using these bio-based materials. So I'm going to go through this as quickly as I reasonably can without losing you. So some of the work that we've done structural testing of straw bale walls, which have led to the bale house. We've loaded them because, as I said, they can be load-bearing structures, and established that really the plaster in these walls is a critical element in the structural performance. We've tested the panels that formed the bale house to see how easy it is or difficult it is to blow them over, and we indeed tested the bale house by pushing the bale house as well with hydraulic jacks, simulating what was reported as a hurricane force wind loading. And at the time, the researcher who did this dressed up in a wolf suit to represent the big bad wolf, and he's now a senior lecturer at the university. And we've done thermal testing on walls to measure the actual thermal transmittance or values, and also acoustic performance, and of course fire resistance as well. So in this case, we tested a full size, there's an errant Bath City emblem there, which I'll explain at some point, but ignore that and just focus on this. This is a 3 meter by 3 meter straw bale panel, a mod cell panel, which has been strapped to a furnace in a standardized fire test. Now, for to meet the requirements of building regulations for the type of buildings we were proposing to use, it needed to demonstrate 30 minutes fire resistance. And we stopped the test after 2¼ hours, and the panel had not failed in that time. So it exceeded our expectations. And in the test, after, I think it was, after 90 minutes, the internal lime render that was protecting, essentially you could say protecting the straw from the fire, fell off. So for the last 45 minutes of the test, it was just the straw that was resisting temperatures in excess in the furnace of 1,000 degrees centigrade. And after 1 hour of the test, with it approaching 1,000 degrees in the furnace, it was only just above the ambient room conditions on this side of the panel still. So it provided very good barrier. There was a number of ways that the panel could have failed that test. I'm going to, in the sense of, we've done tests to look at the durability of the straw and demonstrated that, in fact, it has greater resilience to humidity conditions, and we've been monitoring the bale house and other buildings for a number of years. And really, one of the concerns, of course, is that there's a bio-based material. If it gets wet and consistently wet, it will fail. And if it does, then it will. But so the idea of the design and the use of the materials is to ensure that it stays at safe levels of moisture. This is the bale house with a thermal imaging camera on a cold day in February, and showing that the surface temperature of the panels is very uniform, and really the leakiest elements of the building were the door and window frames of the house rather than the straw bale panels. Those were donated to the project. Bales are made by farmers as a product of agriculture, and of course they're used in horticulture, they're used as animal bedding, etc. So they're often mistakenly referred to as a waste material, and they're not a waste material because they do have value. Straw is sold. You generally don't sell your waste. In the main, you pay someone to take your waste away. But The perception is that the straw here is orientated in a less preferential way. So to look at that, you think, and if you cut that, the straw would appear to be all end on, which is not the way you'd want it, because that would facilitate heat flow through it, because lots of little empty, if you imagine it's formed of lots of little drinking straws, then those air will act as little conduits to allow the air through. So some people have suggested, well, you should turn the bales on their side, because then the orientation will change. But in fact, the orientation is not, is very similar if you lay them that way, or you just flip it on its side. And in fact, the main difference is the heat flow going lengthwise, because that's the way it's manufactured. It's compacted in a sort of a tube and extruded out of the baling machine. So indeed, the best, most optimal way of laying a straw bale in a wall to get the highest thermal insulation would be to cut them in half and to lay them crossways, end on, if you like. And that's what's led to some research work where we've started to bale straw, rebale straw as an insulation product, not bale straw as an agricultural product, and looking at ways of optimizing straw as an insulation material. This is a hemp lime test building, also on the site of what's now the Chancellor's Building, built 2010, and just looking at measuring the performance of the building through making a hemp lime building like this, built and then lime plastered to, well, I think the finished building is there at the beginning of the slides there. And that provided us with a test building for about 18 months, where we could measure the performance of the building over at least one complete year, summer and winter season. We've done some structural testing on hemp lime walls. I'm really going through this a bit quicker now, and also looking at cork building walls as well. And part of that cork building I talked about, we did structural testing there. This building is in Eton, just near Windsor, right next to the River Thames, and it was shortlisted for the Sterling Prize as one of the 4 final shortlist buildings in 2019. We've also started doing some work on mycelium, particularly with colleagues in biology as well, and the opportunity really for using fungi and the mycelium, this, I suppose crudely, the root system of the fungi, to bind together other materials, organic waste materials like chipped up OSB boards, oriented strand board, and other wood waste products, for example, to create a board insulation material. And so technically it's feasible, but no one's been able to do it commercially yet at scale that you could really do it convincingly. Once you've grown this, then you put the product in the oven to essentially kill off the fungus, so you're not taking live fungus into your building. Right. I'm running out of time, haven't I, pretty much? 5 more minutes? Yes. Right, okay. I wanted to talk about, I could get my colleague here to talk about this project, because Francis here works on this, but I wanted to just mention some of the current project we're doing, which is called Transforming Homes, where we are looking to retrofit and remodel existing social housing using bio-based materials, particularly bio-based insulation materials, and what's called, often referred to as a fabric first approach. So by principally improving the energy performance and the quality of the building by looking at the fabric, i.e. the walls, the roof, the floors, the actual structure and external envelope of the building, by improving its insulation qualities, by improving the air tightness, so you're not leaking or using energy unnecessarily, and improving the resilience of the fabric to climate change as well. So we're working in Bristol and in Swansea on homes, and we chose this period of homes. These are homes that were built between the wars, 1920s to 1940s. There are about 3 million of these still in service in the UK. Many of them, I think about 1.5 million, maybe half of them are still social housing. The rest have been acquired under the right to buy. They were classic they were council-built homes built in that period between the First and Second World War. And these homes in particular here shown here are in Knoll West in Bristol, and we're working with communities there, and also in homes in Swansea as well, together with other partners. And the project called Transforming Homes is to work together with the communities to transform their homes, not just to retrofit them, but to improve the quality of these homes. So in a process of co-design, so we're working with the residents, I was going to say homeowners, but the residents, and together with other social landlords, etc., as well, to come up with solutions to improve and retrofit and make use of bio-based construction and other low carbon solutions. So our partners are here. We're working together with what's known as the GW4, which is the 4 universities of Bath, Cardiff, Bristol, and Exeter in that alliance, together with 6 other non-academic partners, including a social group based in Bristol called We Can Make, who are associated with the Knoll West Media Centre and Swansea Council as well. And our process here is one very much of co-design, and we are preparing and getting ready to do some workshops with the residents in Knoll West next week to work on solutions that together with them that they would be happy to use in their homes. And that's a 2-year project. It's 6 months in, so we've got another 18 months to run. So just closing comments about bio-based building materials going mainstream. I've been working in this area for probably 30 years. So before I came to Bath, when I was in Australia, I was working on straw bale construction. Things have changed. I think when I first arrived in Bath, I was definitely seen as the hippie in the department, and what you're doing working on straw and mud, because that's not going to catch on. It has become more credible, but it's still in many ways a niche in the market compared, a teeny tiny part of the construction market. And there are lots of opportunities for these materials to really gain a greater share, but we must address some of the issues around these. Some of them can be addressed more easily through science and addressing issues about durability. Others are around manufacture and being cost competitive as well. And we must make optimum use of these materials. So when you got straw, if you can use it as a load-bearing material and as an insulation material, why not? Because you're reducing costs rather than just using it as an insulation material. And just as a contrast, the market in the UK for bio-based insulation materials has gone from pretty much nothing to a tiny share of 0.3%. Most of this material, like wood fibre insulation, sheep's wool, well, sheep's wool less has been imported, but it is changing compared with, say, France, where it's up to 10% of the market, and that's partly because the French government have subsidised and supported that, and we haven't yet. And just to show that, as well as research, this is my straw bale shed at the bottom of my garden, which was very useful during COVID, because that was my office as well. It's not to say it's a straw bale shed, it is, this wall is straw bale. I live in Oldfield Park, East Twerton, so my garden's only 5 meters wide. So to make all my walls straw bale would have been a bit much, but I have the depth in the garden to make that wall straw bale. And I'm monitoring that building. And I've just recently insulated one of my rooms and started to insulate my house with wood fibre insulation as well. And I thought I'd give it a go myself, and it's so far so good. And so I'd recommend that's with wood fibre insulation as internal insulation. I suppose what we're trying to do with the social housing project is to try and do external wall insulation as much as possible to minimise disruption. Because if you've got 3 million homes to work on and all those families need to move out of their homes for a period of time, decanting those, there's nowhere for those people to go in many cases. So we're trying to minimise disruption as much as possible. Whereas I just kicked my daughter out of that room when she moved out a few years ago. So that was a vacant room. But yeah, right, I'm done. I'm sorry for overrunning. Thank you for your attention and staying and not leaving. and I'll answer any questions I can. Thank you. And there's people who've worked on this and supported it.
I'm just coming here to use the microphone because I'd like to encourage those people who have listened and watched online to submit their questions through the Zoom chat facility. If you would do that, then as the Q&A session runs along, I'll look for your questions online. Okay. Perhaps you'd like to field your own questions, and I'll go around with one.
Could you say something about the costs involved? I mean, I would have thought this ought to be really, really cheap, and yet you're saying it's cost is a problem.
Yeah, that's a good question. I mean, it depends on what materials we're looking at, but for straw bales in themselves are relatively inexpensive material, but there are relatively few suppliers in terms of taking a bale and turning it into a building. So the prefabricated approach is, and it's related to scale of manufacture. So at the moment, most of these might be considered prototypes. Once you've turned it from just taking the raw material, the straw, and forming prefabricated panels and erecting it, hiring the cranes, it's at this stage probably more expensive, not radically, but more expensive than other forms of construction. The wood fiber insulation I showed there is more expensive than some other forms of insulation material as well, but not so much to not prescriptively more expensive, but enough often in an industry where it works on very fine margins. So if anything is, say, 5 or 10% more expensive, it's hard to argue to use that material. So I think there's a variety of reasons why it's some of them more expensive. Limited supply chain. I think if you buy straw bales and decide to do it yourself, and you can make the building very cheap, I think. But if you get a contractor in to do it, you're probably going to find it more expensive.
Hi. Is part of your research program done with end users, be that construction firms, architects, or end users as clients? If so, what are their main objections and how do you counter them?
Sure. Well, in terms of the latest project, which will go back here, so the ones we're working in the communities in Bristol and Swansea, absolutely, we are working with the residents of these buildings, and we're very much working together and control and governed by what they want, because we're doing demonstrator homes in both Bristol or we plan to in Bristol and Swansea, and we are very much recognize these are people's homes that we are experimenting with in some ways. So we're very much aware of that we've got to recognize and take account of their wants, their desires, their concerns, etc. And in much of the research, yes, I've been working together with structural engineers and architects. Often architects and the structural engineers are the ones who are the innovators and the promoters of these. And where it's worked most successfully is where the clients have understood or wanted the material. And sometimes where projects have gone wrong, maybe the materials and technology have been foisted upon them without fully understanding what the potential risks are. But very rarely of projects have gone wrong, the significant problems. I think most of the projects, I would say, have been successful, but concerns are of the usual ones of bio-based materials are, durable. Is it going to last? Is it going to get wet and rot? Is it a fire risk? Is it going to burn down? Are rats going to move in or infest my walls? Am I going to get insurance for the building and things like that? And I think, we can reassure people that yes, you can. But these buildings do require maintenance as well. You know, not, and all buildings require maintenance. Nothing's maintenance free, unfortunately. Some require a little bit more. I mean, I think the key to sustainable building is to create beautiful buildings and buildings that we want to maintain and care for, and not, and whatever the opposite is of beautiful buildings, ugly buildings, or ones that we don't care for. So if we build buildings that we love, then we'll look after them, like we have, I suppose, with Bath as well.
Thank you, Pete. I've got 2 questions. One is about that decrement delay issue, which is, could you just say what the comparison with sort of concrete walls and normal?
Well, I mean, the comparator we used, well, I mean, part of the reason why, I mean, I'm sorry that I've tried to cram too much into this, and I did rush things a bit, so I apologize for that. But basically, so we started off at time 0 that the temperature and humidity conditions either side of this panel were the same, and then we made it very cold on the outside, which was the inside the chamber. And so what you would ultimately expect is that I'm going to move away from this, excuse me, that you get there'll be a linear thermal gradient across the wall. And so ultimately we'll reach about 1 degree on the outside face, and this is the fabric surface of the wall, and on the inside it's 20 degrees. And say from a slightly wavy line, it pretty much got there. Part of the reason why it took so long is it, in contrast to other non-hydrothermal materials, is that it's not just about heat flow, it's also about moisture flow. So there's water vapor inside the pore structure of the hemp lime. So when there's moisture, when there's heat change, there's also moisture movement as well. And that's what contributes to this decrement delay or hygrothermal inertia. And all we compared it with was with mineral wool, which is well, a mineral-based, you know, a famous brand is rock wool insulation. A lot of us have probably got it in our lofts and stuff. And it took only 24 hours for it to get to the same steady state condition. So what we're arguing is that the slow response of these walls to external changes in our climate means it helps protect the internal changes. So if we get a sudden temperature change outside with a 300 millimeter hemp lime wall, it suddenly goes to 0 for some reason, or very close to it. We aren't going to suddenly feel that, you know, 5 minutes later. It's going to take time for that temperature change to come through the walls. I mean, it also depends on how else the fabric of your wall is made up, the windows, etc. But in terms of the hemp lime walls, it takes time. And because, you know, once the decrement delay is more than 24 hours or so, then you've gone through a whole diurnal cycle again. So you would never reach these steady state conditions.
Thank you. And the second question is the carbon emissions sort of life cycle for new build. So how much are you saving both in construction and in life cycle emissions are you estimating for these new builds? And what are you hoping to save in the retrofit you're doing in your latest project?
Okay, let's go back to this building here. Where's it gone? The Bale House. This had a net storage of carbon if you took account of the biogenic photosynthetic carbon. So even of the straw and of the timber, then the net carbon emission footprint of that building was negative. I mean, now it's a slight contradiction because any emissions is negative in terms of the climate, but it's a carbon store. It's banking the carbon dioxide that those plants have absorbed during their growth. And I think it was something like 90 tons of carbon, something, no, maybe not 90, but I can't remember exactly. It was equivalent to something like 10 years of operational energy for that building. So our aim with the retrofit is also to use bio-based insulation materials and ideally not have a net emissions as a result of improving that fabric. because using some insulation materials, rigid foam insulation materials, for example, but not only, some studies have suggested that the carbon emissions of the manufacture and installation of those systems have been greater than the carbon saved if they'd have continued just using their gas boiler without that insulation. And that's not what we want. We want a net carbon saving. And part of that is through using bio-based insulation materials, as well as reducing the energy performance of the building, the energy needs of the building, and shifting away from fossil fuel energy systems to ones based on renewables and electricals as well. So it's a combination of those solutions. But ultimately, to come away a solution, a target for the retrofit is that there is a net zero solution. Now there is my colleagues who do life cycle assessment, life cycle analysis, concern the over-reliance of biogenic carbon, because ultimately the straw in these buildings, the timber in these buildings, at some point in the future, whether that's 60 years, 100 years, 200 years, 500 years, will potentially break down because the buildings will not necessarily because they fail. They might fail because they're not being maintained well enough. Without dwelling on that image, but they will, you know, we may get tired of them. They no longer suit our purpose, and that carbon will be re-released, and that is true. The counter argument to that is that I think the challenge now is to store as much carbon as we can, and then in the future, hopefully, when we're less reliant or stopped using fossil fuels, we can maybe afford to release some of this carbon that's locked up in our buildings. But at the moment, it could be a very valuable carbon store, say for the next century or so, to get us through the worst of what we're facing at the moment. And if we, you know, there's no reason to say the Bale House, if it's well looked after, cared for, maintained, that it wouldn't be there in 200-300 or years time. The oldest timber buildings are over 1,000 years old, and so there's no reason why I don't think that building wouldn't be there. Could easily be there in 1,000 years time if we wanted it to be.
Can I ask about various hazards? You stress test for physical strength, mechanical strength. What do you do about biological hazards, invertebrate infestation, or indeed the rats?
The rats, yeah, the rats.
You put rats in and see how long it takes.
We haven't done any live experiments with rats. No, I think I haven't gone down the ethical applications of doing that. I think we designing it out to avoid rats getting in the walls as much as possible. Now I know, you know, some people will repute that rats can eat through concrete, and I think they possibly can. They're certainly remarkable animals, but that's primarily through design and good maintenance. Is the way that we've dealt with, and we've not in any of the buildings that I've worked on come back and said, well, we've got a rat infestation. So I think it's with good diligent design to minimize access routes and things into the building. I mean, my own modest shed, I was also wary of potential of rats, and so essentially it's very simple. It's a 15 square meter building and stuck at the bottom of my garden. Where's it gone? It's right towards the end there. And so the solution this is just a timber frame building, and then straw is in between the studs here, and then there's a membrane on top of the straw, and then the battens, and then this timber cladding. And I've put a wire mesh under there to stop any animals or anything getting under there, and it's sort of getting nasty, unpleasant, sort of sharp mesh that will hopefully, and I haven't as yet had any issues with gnawing or rats in there yet. But yeah, I mean, I think rats, you never say, you know, rats are around. The other thing that we have experienced in some of the buildings, the rendered buildings, or the wet plastered buildings, and this one is dry lined just with OSB, is book lice. That was the infestations of book lice, which are these tiny little insects. And apparently with the damp plaster, there's enough sort of germinating little mold spores in the atmosphere with mold, and that would provide the sustenance and nutrition for the book lice. But they would sort of like have one generation and then die. So, you know, the solution for book lice was just a vacuum cleaner, because they wouldn't last very long, and you would just go along if you could tolerate that, you know, and that wasn't, when I say an infestation, it's noticing a few insects crawling around, tiny little things that, well, I suppose if you've got lots of books, you may have seen them in your books, but yeah, that's what they're most associated with. So I haven't really experienced anything particularly and I think, yeah, with having measures to minimize the risk that rats or mice could get in your walls is a solution.
I've got a question, Pete, and I have to confess I work with Peter on the Transforming Homes project at the moment. But in answer to the question from this lady here about why who's engaging with these materials, part of the project, the community project, got people from Knoll West to go to a recent sort of Energy Plus conference in London called, I'm trying to think of the name of it, Pete. What was the place you went to? Future Build. And the residents who went were just amazed at the bio-based materials that were available, and they just never knew about them. And we're hoping to engage with them further to develop their choices as to what they would like. And I guess people just don't know what's out there. And that's my initial take from that. You know, I'm a building engineer, I know what's out there, but residents really don't know what the options are because they're not available in your local builders merchants. That's the first thing. The second thing I want to say, Pete, is on fire. And if we're limited to 8 meters, 18 meters, but you showed us a demonstration of 1.5 hours fire test and still was just above ambient on the inside. Why is that the case if it's shown from that test that straw bale can perform?
It is related to, yeah, the concerns over the Grenfell disaster, where we saw the fire spread up the facade in that retrofitted tower block, and that wasn't bio-based insulation material, but it was flammable building material. So I think for the moment, the precautionary approach is to limit it to buildings of 18 meters for that spread of flame, and that may change. And there are timber structure buildings, so you know, like I won't go there, but the building right at the beginning, which was at the University of British Columbia, I think the tallest timber building in the UK is 9 stories still at the moment. The tallest building in the world is well over 20 stories of engineered timber construction. And it's mainly in the facade that is the particular problem and the concern, as we observed at Grenfell, where the fire chased up the outside of the building very, very quickly. Things may change and hopefully will, with more understanding and knowledge and ways that we can deal with this. But for the moment, we can't build facades over. I mean, but 18 meters is still, you know, as I say, 5-6 story building is still. There's a lot of buildings where we can use bio-based building materials.
I have a online question here from Anne French, who says, could you just say a bit more about cork as a material? She seems to be under the impression that it's exterior attached insulation, but I thought that from what you said that it's actually a constructional material.
Cork, and in this case, these blocks are cork crumbs, so they're the poorer quality granulated pieces of cork, which aren't good enough for bottle stoppers or for shoes or other fashion items, and a variety of other uses like cork mat or flooring. Larger crumb, which are then put together and compressed under heat and pressure to form these blocks, and which is why they're slightly sort of a darker sort of chocolatey brown color. And they are used as insulation material fixed onto facade or onto the substructure of buildings and a variety of uses. And then on top of that, sometimes they can be plastered and rendered directly on top of the cork. In this particular case, the architect wanted to demonstrate that you could make an entire building out of cork. And so these blocks here are like Lego blocks. They are profiled and they're dry stacked, and the thickness of the wall, and they're 0.5 meter thick. There's a lot of insulation in there. And it was really just, can we do this? And so the building is designed particularly like this. So the corbel sort of roof is to enable that you could also get a roof structure made of the cork and not go to a timber roof. And then the skylights on here are obviously to get light into the center of the building, but also to act as weight, because one of the things about cork is it's relatively light. So to structurally be stable and to resist wind forces, you need some weight on there to help stabilize. But also around the top of the walls is a timber ring beam, a continuous timber beam, and there are steel bolts through that cork to tighten it down as well, because it is a very lightweight material. The floor is on a lightweight screw piles on the floor, and yeah, it's built about 20 meters from the Thames. So if it ever does flood, it just floats away, I guess. And you know, and it was a prototype building. So again, go back to the question like cost. This would be very expensive. These blocks, they're made in Portugal, where a lot of the sort of cork forests are. Although we do have a cork oak tree growing on campus, which was planted in memorial of a colleague who died a few years ago. But it's slowly growing. But I don't think we'll ever get around to harvesting any cork on it. But it is surviving our weather conditions, despite I suppose predominantly the wet at the moment, rather than the cold. But yeah, no, this is an interesting example. There was we did a lot of testing and profiling those Lego joints to ensure that the rain didn't come through the joints. But in fact, in testing, because the way the cork was corbelled and the porosity of the cork, actually the rain found an easier way, and that was to go directly through the cork in the roof structures, which is why you've got these timber strips on the roof to provide that weather tightness. Yeah. And that was 5 years ago. I imagine that the cork has probably grayed off a little bit now. I haven't been back to look at it, but I think, as far as I know, I think it's working very well. I think he built it on his land. I think he's probably turned it into a granny flat.
I'm going to claim the privilege of asking the last question here. What really strikes me about all that you've been saying is that you're having to address the uses of these biomaterials as a bit like making a special suit of clothes. This is not mass manufacturing yet. And yet, every day, builders use mass-produced biomaterials in the form of particle boards of various sorts, engineered wood stuck together with glue. And nobody questions this at all. Nobody would even think of it as a biomaterial. And that's because it's available off the shelf at the builders' merchants in huge quantities. And I just wonder whether you look forward to these kinds of materials being available in that way.
Well, some of the products to talk about, particularly the insulation materials, are available in those type of quality. They are manufactured at scale at the moment, mainly in Germany, but in some markets, you know, as I say, in France, 10% of the market at least is using these materials. So yeah, you could go to a general builder's merchant and buy wood fibre insulation and put it in the back of your van and drive off and go and use it. You can't in this country at the moment. You can buy it, but it's a small number of specialist suppliers. Yeah, I can foresee that will be the case, and I think some of these other materials will as well. I don't think we'll ever be going to builders merchants to buy straw bales, not in the sense of the way they're baled at the moment, but straw-based products. And one product that was quite well established in the years post-war that got discredited by the 70s, 80s was something called Stramit, which is compressed straw board, which essentially was compressed wheat straw and then lined with paper, and was used primarily as a sort of as part of roof structure, sort of span distance between joists and stuff. And then there were problems with it when it got wet, and like any bio-based material, if it gets substantially wet, particularly in a flat roof, it will fail, and the straw and the binding and the adhesion of the straw together will start to fail, and you have problems. And people say, well, that's the problem with the Stramit, and that's discredited. But actually, it failed because the roofing membrane, the felt or whatever was there, was failed, and the water got in. The Stramit failed as a result of something else failing. So there's not an intrinsic problem with the Stramit, I don't believe, in that sense, but people see it as a problem. They still continue to use roofing felt, and it still leaks. But they stopped using Stramit because they see the consequences of that. So it's about perception, yeah. And I mean, there's a building on campus which has got Stramit board in the roof, or did have. I think it's being removed at the moment. But it's been there 50, 60 years quite happily. And then the roof has leaked ultimately. So I think there are scope for getting products like this, definitely. Down your local Travis Perkins, etc. Other building merchants are available as well. And certainly, I mean, you can now go to Travis Perkins and others to buy bags of building lime, which 10 years, 5 years ago, perhaps you couldn't have done. I think Bath is a special case because of the historic fabric and the conservation buildings, but you can buy building materials that fall under this sort of general, which were considered distinctly alternative or conservation, that you wouldn't have got at general builders merchants until relatively recent. So the things are changing slowly.
Thank you very much. I think we've all learnt a lot. I feel very optimistic.